Today's video is all about something I've wasted way too much time doing for my own machine learning projects, and that's hyperparameter tuning. We'll use the Tidymodels packages tune and finetune to effectively and efficiently search for the hyperparameters that will take our good machine learning models and make them great. Let's dive in. In our last video, we covered the MLOps cycle, starting from understanding and cleaning our data all the way to model monitoring. In today's video, we'll focus on training and evaluating our model with a specific focus on hyperparameter tuning with the Tidymodels packages tune and finetune. Before we get into the details of the implementation, I want to give my thinking around how we should approach hyperparameter tuning overall. It's an important skill, and one of the main outcomes from this is that it boosts our model performance as compared to no hyperparameter optimization. There's an important caveat to keep in mind with this, though, which is you can end up wasting a lot of time if you don't take an intentional and systematic approach to this tuning. Fortunately, the tune and fine-tune packages are what provide that approach using the Tidymodels ecosystem. We will be using some of the code from last time, specifically things like loading in packages, exploratory data analysis, and importantly, preparing and splitting our data into a training and test set, as well as creating folds for our cross-fold validation that we'll get to later in the video. You can dive in, of course, I'll link all of this below. You can dive into these details if you'd like, but I'm assuming that you've already run this code at this point in the video. Okay, so now with these splits established, we can go ahead and create a recipe here. Much like last time, I'm not going to be covering details of the recipe, but I have some links that can help you get started, make some recommendations for how to order your steps, as well as make some recommendations for model-specific pre-processing steps or feature engineering steps from the fantastic text Tidy Modeling with R. For our specific recipe here, all we're going to do is use our output variable sex, include all of the other variables that we have in there, and then I have one additional step to create dummy variables from our species outcome, which is really an optional step based off the model type that we're going to be using. And that model type is going to be a gradient boosted tree. This also will introduce a new package. It's an extension of the parsnip package for model building called Bonsai. So tree, bonsai, get it? We will need to install the engine, the pack that has the gradient boosted machine model. In this case, we'll be using light GBM. That's what that first line of code here is doing. But I want to specifically draw your attention to some of the tuning steps that we have in here. Specifically, we have our learning rate, our stop iterations, the number of iterations before halting, as well as the number of leaves. Each of these are parameters for a gradient boosted tree. We won't talk about what these are doing here, but suffice it to say we have three different parameters that we want to perform hyperparameter tuning on. So let's talk about how we can go and do that. We can use some helper functions from the tune package to look at the details of these hyperparameters themselves. So the first thing we're doing here is using the extract parameter set dials function, and we can see that we have these three components, these three hyperparameters, of course, that we're going to go and optimize here. You can look at each of these individually to see the default ranges on them. So looking at specifically the number of leaves, this can range from 5 to 100. If you want to tweak that, you can certainly do that, though for today, we're going to leave all the defaults as is for these parameters. Next, we want to create a grid from these hyperparameters, and there's another convenience function that has a fancy sounding name, grid Latin hypercube. What this is doing is creating a space filling design for our grid that will then be used for the tuning action. The size parameter here, so 50, this is the number of parameters, so to speak, that we're going to be testing for this. How big that is really going to be based off of your patience. More to come on how to make this go faster in just a few moments. we can see the results from this. So there's 50 rows that directly corresponds with the size argument in grid Latin hypercube, where we have the learning rate, the stop iterations, and the number of leaves with example values from each of those here. These are going to be passed directly to our tune grid function, and these are the hyperparameters themselves that will be tested. Okay, so before we actually get to the tuning step, we need to create our workflow. We'll add our recipe that we created a few moments ago, as well as our model. Next, we want to add some additional customization to how the tuning is going to run. Relatively simple here. We're just going to save our predictions and save our workflow. I won't talk through those for the tune grid example today, but there's great documentation on some of the other parameters as well. You can control how verbose the output is, as well as control some of the parallelization to make this optimization run faster. Here's the actual code itself. We pass our BT Bonsai workflow, so the workflow that we just created, we pass this to the function tune grid. This has 3 components to it. The first is the resamples. So these are the folds from the cross-validation that we created in the previous video. We have those grid tune that we created with the Latin hypercube call, as well as the control parameters for the control grid function that we created. So we have our resamples, we have our grid, and we've set our controls. And here's what an output could look like for this. Much like many of the other aspects within Tidymodels, there's convenience features here. So we're using the auto plot to show us the impact of changing each of these hyperparameters on our overall model output. We're looking both at accuracy and the area under the curve for the receiver operator characteristics, so ROC, AUC. These will certainly correlate strongly with each other in terms of the overall performance. And you can see that we have a substantial impact from our learning rate. This is the hyperparameter plotted in the middle here, with some mixed results for the number of leaves and the number of iterations before stopping. Okay, so that gives us an idea of what hyperparameters to choose, but you notice that, especially say, for example, at the earlier learning rates or the learning rates at the more negative values here, we likely wasted a lot of time by looking at hyperparameters that were unlikely to be helpful for us. To better perform hyperparameter optimization or tuning, we can use the finetune package to do what's called racing. Racing will perform a series of model fits, compare them, and then down select of what to include in the next iteration for the fine tuning. In practice, what this does for us is reduces the total number of models that need to get fit. Let's say we have 10 folds and we have 50 hyperparameter sets that we've specified. That's 500 models that were run on the previous iteration. We can use racing to reduce the total number that actually have to run. Same settings here, although we're using control race instead of the control grid. And then we can run it much like we had before. Instead of passing the workflow to tune grid, we pass it to tune race ANOVA. So we have our folds with penguin folds, our tuning grid, and then the race control to go ahead and kick this off. This looks a little bit different than what we had before. It can actually be a little bit harder to interpret looking at the impacts, the marginal impacts of each of these hyperparameters here. It again looks like it's a little bit all over the map in terms of the trends with the overall performance. We can actually look at this a different way as well using the plot race function from the tune library. And this is showing the resamples, you can think of it, that are being used as a function of our metric, which is the ROC AUC again. You can see the hyperparameters that basically fell out during these race conditions. So when we did this with the tune grid function, so just the base tune, we actually were running all of these, so we weren't cutting some of these off early. One way to think about this is that from the model performance perspective, all of the points here, these are the ones that are above, say, about 0.93 or 0.94. These are the ones that are included for subsequent testing, and you ignore the ones that weren't performing well for subsequent testing overall. So that's one way that we can speed up these, is by using the tune race, the racing conditions from the finetune package. Another way that we can do this is actually to use parallel processing. The results from that initial stage can all be run in parallel, and so we can. What this allows us to do is, using a similar or even lower number of model fits, we can actually get to a better hyperparameter optimization. Let's see what this looks like in practice. Instead of specifying a size of 50, we've increased this 5 times to 250. And we're going to use the do.mc library to actually run this in parallel. I have 10 cores available in my system, so I'm using that register do.mc function to tell it that I have these 10 cores. Much like we did before, we can pass this into the tune race ANOVA function, where we're using our big grid, so the one with 250 models. So this would be 2,500 model fits if we used the tune grid approach, but by using tune race ANOVA and running this in parallel with just a minute or two of patience, maybe a little bit longer than that, but certainly less than 5 minutes, we can fit all of these models, and here's some of the resulting outputs that from that. If you compare this to the auto plot that we saw for just using the race ANOVA, you'll notice that there's just more points here, right? We're fitting more of these models. We've explored more of our space overall, and we can use this to actually, before I get to that, we can show again this racing impact here. It looks similar to what we saw before. It's just now we have more lines here, so we're fitting more models, and you can see a similar drop off as you go through the different stages. So overall, this gets us we can go and look at the final model performance. So we can select this with our output ROC AUC. We can extract that. This is the same approach that we did with the MLOps overview in the last video. So we extract the model ID, and then we're going to refit the model using our test set data in addition to our training set to fit the full model, selecting the best model from our hyperparameter optimization. And we can see what the outputs look like here. So our performance, it looks like we have a accuracy of 90.5% and an ROC AUC of 97.3. So this is, I think, about as good as we could hope for this Penguins data set here. And just to round it out, we can look at sorry, there we go. So let me move this window a bit so you can actually see the full plot. We can see a rock curve here. And again, this is about as good as I think we could hope to see with this data set. All right, so 3 key takeaways from today's video. Number 1, use tune and fine tune to perform your hyperparameter tuning. This gives you that systematic approach to efficiently explore your hyperparameters, the hyperparameter space of your model. Number 2, use racing functions like the tune race ANOVA from the finetune package to screen the hyperparameters that are most likely to perform well for your model. You can also dive deeper into the finetune package to look at other racing functions. There's a win-loss one, as well as a few others that I'll let you explore on your own. Finally, use parallel processing whenever possible for this hyperparameter tuning steps, especially for these grid-based approaches where many of the model fits can be done in parallel, and you'll see sometimes 10 or maybe even 20x improvement depending on the configuration of your system, so you don't spend a lot of time waiting around to optimize your fit overall. All right, so let's take a brief moment to talk about where we're going next. All that I've talked about today in terms of hyperparameter tuning was a grid search-based approach. Next time, I want to talk about iterative hyperparameter tuning using techniques like Bayesian optimization. That's it for today's video on hyperparameter tuning. I hope you enjoyed it, and if you did, please consider giving it a thumbs up or subscribing, maybe sharing it with somebody else who might enjoy it. I'd love to hear about your own experience with model building. Have you used alternative hyperparameter tuning options? Have these worked for you? What other tips did I not include in this video that you think others should be aware of if they're doing hyperparameter tuning themselves?